compartments, then you're wasting time. Okay, it has to be either curiosity-driven research or utility-driven research. Now, whatever be the research, okay, you will have to validate your claim, and the claim is typically on a restricted setting. Okay, it is impossible to capture the whole reality, whatever the field of research. And claiming that the observational hold for the whole population is a very big leap of generalization. This is called leap of generalization. Okay, and there you need this machinery of hypothesis testing. Otherwise, nobody will believe you. Okay, the claims will not be scientific. That is the important point. Hypothesis testing is an exercise similar to proof by contradiction, as you see. Okay, our goal is to goal always is to throw away the null hypothesis in the face of the data. Okay, so null hypothesis has a very interesting fate. It is born to be killed. Very strange, right? It is born. It takes birth with the explicit aim of being killed. So that's straight. And then we have type 1 and type 2 errors. These are always with respect to H0. If we assume H0, then what is the amount of error and which kind of error? Type 1 error is when we erroneously reject H0. Type 2 is when erroneously accept H0. Okay. So this is a one-slide overview of hypothesis testing. Do please remember everything here and then dig deeper. Any question from anybody? Okay. Let's take up this very interesting discussion, ChatGPT giveaways. Now, you know, a very pressing problem in front of everybody, academic community, school teachers, college teachers. So, you know, wherever any kind of writing is involved, key question is the writing original from the writer himself or herself, or is it from ChatGPT? A very important question. And softwares are being written by Stanford, MIT, Harvard. Apparently, they have very powerful softwares. And apparently, there are tools also on the internet to check if the writing is from ChatGPT or for human being. Of course, these tools are not completely 100% correct. But I'm told that this top universities tool, which they do not give out, okay, the mechanism of, are very accurate. So this is a newspaper report from Times of India on 13th October. Teachers have this difficulty, own writing or result of ChatGPT outsourcing. Okay, so in our department also we have been discussing in faculty meetings what to do about what stand to take with respect to ChatGPT writing. Now the observation is that there are giveaways, words that ChatGPT over relies on. So ChatGPT's outputs typically have a preponderance of a few words, okay, some words, which are kind of giveaways. Okay, by looking at them, you can begin to suspect is it from ChatGPT or not. So it seems since 2023, the appearance of Dell has become very frequent. Dell. And there's this Professor Jeremy, I don't know how to pronounce this, Nguyen maybe, of Swinburne Business School, Australia, finds the use of this word increase exponentially in PubMed. PubMed is a medical text repository, completely open and free, and is an extremely valuable source of information for medical researchers, especially for bioinformatics, those researchers who are working on text mining for medical domain. So PubMed, and you know, surprisingly, for NLP researchers, most of the time, a very big challenge is the quality of the corpus. Okay, so many times we have to deal with extremely noisy text, very incomplete, lots of spelling mistakes. But PubMed is absolutely clean, beautiful text. Okay, in the health domain, I really invite you to look at PubMed to see how a very difficult domain is written about and expressed so nicely. Okay. Now, now we are seeing that, and PubMed is an ever-growing repository of text. So this professor says that since 2023, there has been an exponential increase of the word del in the PubMed corpus. So most probably people ask ChatGPT to write a piece of text and then modify, update, refine, and add it to PubMed. Additionally, nevertheless, a testament to it is important to consider these also have increased quite a lot. So these phrases. This is pointed out by a data analyst called Margaret Efron. Okay? So these phrases also have become much more compared to pre-ChatGPT era. And the sentence structures often are overly complex. Lots of clauses, lots of long-winded expressions. And many times the tone is very formal, and this doesn't resonate with the situation. Suppose there is a conversation between two friends, and suppose the text is extremely, formal, then this doesn't fit in the situation. Okay, so that is another point which has been seen in ChatGPT's output. Takes a very formal tone, even though the setting is very, very informal. Okay, so this is an observation. Now, and there has been an overuse of the words like realm, intricate, showcasing, pivotal. A Stanford study points out that the use of these words exploded since ChatGPT. Okay? Through an analysis of millions of words, huge amount of corpus has been analyzed, and it is seen that the frequency of these words have increased exponentially. The use of these words exploded since ChatGPT. Which are the words? Realm, intricate, showcasing, and pivot, apart from the phrases that we saw. Many AI detection tools are online, but they are also very vulnerable. Similar situation exists for AI images. And there, very interestingly, hands are giveaways. Okay, the hands are placed very awkwardly many times, not naturally. Anybody who looks at, anybody who is trained in drawing pictures, looking at pictures, analyzing pictures, say that this hand is not looking right. Just like we say this word is not sounding right, a phrase is not sounding right, the hand is not looking right. Now, there is an interesting related situation to this, which is very interesting. I would like you to think about it. So, if you have seen, if you have read about the actors, actresses in their initial career, okay, what is it the actors and actresses find most difficult? Okay, if I'm asked to come to the stage, okay, and asked to act, most of the actors, including Charlie Chaplin, if you read his biography, says that they do not know what to do with their hands, how to place the hand. How should I hold my hand? So I'll come and stand here, and I really do not know what to do with my hand. Is it all right? Should I hold it this way? Should I hold it this way? This way? Okay. So hand is a very difficult organ to handle. Okay. And this is interesting that in LLM generated images, we find that hands are awkwardly placed. What could be the reason? Okay, these LLMs are trained on images with hand. Okay, and many of those images must be having hands. Most of them will have. Do you have any theory as to why hands are giveaways? In fact, for all these giveaways, you should dig deep, think deeply, and come up with an explanation. Why has become suddenly so prominent? And remember that LLM's output is purely a function of what it has been trained on. Any idea why hands should come out in awkward position? I don't know the answer. Okay, so I was trying to see if you have anything to advance. An artificial picture typically makes mistakes in the hand. Okay, think about it. And many times the text image combination becomes nonsensical. It's a multimodal output. There is no consistency between the image and the text. So it is known that the large language models are still struggling with dealing with multiple modes of information. Okay? And then sometimes the picture is extremely perfect, too perfect to believe it to be real. And many AI detection tools are online, but they are vulnerable. Okay, so this was an interesting report in the newspaper, and lots of such reports in the blogs and so on. You probably are looking at them, but this is a very interesting thing. So I would like to invite you to think about why these are giveaways. Let's move to the next interesting topic, the prompt and pramana. So here we would like to look at the Indian Indian inquiry into the nature of knowledge and how we acquire knowledge. A very profound topic. How do we acquire knowledge? From what sources? What is their authenticity? A very profound topic. So this is called pramana. Okay, the shastra is called pramana. Now, and this is also a Times of India article by Bindra and Saxena. Prompt AI, these pramanas. Many intriguing connections between AI and some of our ancient texts. So pramana means the means of acquiring knowledge. Okay, how do we acquire knowledge? So the Shastras, the scriptures, actually list the following sources of knowledge. The first is pratyaksha, the most important source of knowledge. This is due to perception, through perception, direct sensory experience. So for example, we have the knowledge that fire is hot. This is directly through sensory perception. Okay? Of course, it will be risky to experiment, and we often rely on our parents not to touch fire. So what this is on direct sensory experience. Next is anumana, which is inference. And that depends, that is actually reasoning. We know that one of the weak spots of large language models is reasoning. Not yet able to do very sound reasoning and complete reasoning. So, so seeing smoke, we infer that there is fire. So this is such a frequently used situation that it has become a phrase now. Parvato Bandhiman Dhuma. Parvato Bandhiman Dhuma. Parvato means the mountain. Bandhiman has fire. Dhumat because of the smoke. Because I see smoke, I infer that the mountain has fire. This phrase must be at least 3,000 years old. Okay, so Anumana was recognized as a source of acquiring knowledge by Indian mind very long back. Of course, it happened in Greece also, but later. Pratyaksha, Anumana. And while you are looking at this, please think about LLM all the time and generative AI and AI agents all the time. So Pratyaksha, good, very good. LLMs are very good. They are very good in retrieval. Extremely good. Anuman, weak spot. Upaman, comparison. Know the unfamiliar from the familiar by feature matching. For example, you learn what a zebra is from the knowledge of horse. Okay, zebra also has 4 legs, can run, is vegetarian like horse. So you do feature matching and say that um, um, I have seen this new animal. It is like horse. It runs like horse. It eats grass, fruits, and so on. Only thing is, it has stripes on the body. So it must be new animal. So this is called upamana or comparison. Okay, very important process in knowledge acquisition. Next is shabda, the verbal testimony, knowledge from trusted sources. So why is it called shabda? Why verbal testimony? Do you know why? The knowledge, the definition is knowledge from trusted sources. But what is verbal about it? Yes, India did not have a written tradition. for a very, very long time. Okay, everything was oral knowledge and passed down from generation to generation. That's why there was so much importance given to rhythm, chandam, and also chandas, and also diction, proper diction. Okay, and very clear division of sound. Pa, pa, va, bha. There is a name for each of these sounds. Okay, so these called shabda, knowledge from trusted sources, for example, from very authentic texts. Arthapatti, that is postulation, explaining something unobserved, the hidden variable, from the observed. Okay, you have done post tagging assignment. The post tags are hidden variables, no? Hidden states. So that you inferred from observation, which is words. So somebody is growing fat and is known to be fasting during the day. Why is the person getting fat? Must be eating at night. Okay. So that's called arthapatti or postulation. What is the difference between anuman and arthapatti? Anuman is also interesting. Okay, so anuman is deduction from general to specific. Arthapatti or postulation is induction from specific to general. Arthapatti or postulation is anuman is typically not. Okay, and the final one is anupalabdhi. Upalabdhi is getting. Anupalabdhi is not getting something, so non-perception. Knowledge from absence. Typically acquire knowledge from presence, but this is also very interesting. This is knowledge from absence. We find a gap in the library rack, then we know that the book is missing. Okay, so this is a very beautiful list of the sources of knowledge. Let us remember this in this age of LLMs and generative AI. So the authors go further and see the application of pramana for autonomous vehicles. I would like you to think about pramanas in the context of natural languages. Okay. So what does an autonomous vehicle do? It slows down at zebra crossing, thinking that there will be pedestrians crossing the road, stops at signals, swerves around obstacles, adjusts to unexpected changes. So all these are expected from autonomous vehicles. What is the autonomous vehicle source of pramana? That is source of knowledge. First is pratyaksha. So autonomous vehicles are fitted with sensors, cameras, and leaders. So those are their sources of perception. Anuman do autonomous vehicles do inferencing. Pedestrian nearing the street, slow down. This has been possible to implement in autonomous vehicles. Upamana is comparison. Stop for zebra from the experience of stopping, seeing a horse last time. It has not been done yet. Okay, the autonomous vehicle will stop seeing a zebra because last time it had seen a horse and it was stopped. This is Upamana comparison. Shabda or verbal testimony. The autonomous vehicle is trained on large data sets. So the data sets are its source of data essentially. Now, is it authentic? The authentic word is quote unquote. We know that training data need not be completely curated, clean, high quality. No. For example, learn to recognize stop signs from labeled images. Right? So this is an instance of Shabda or verbal testimony. Arthapatti postulation, currently very difficult. Explaining something unobserved from observed. That was the definition of postulation. A cop waving the cars around in a scene of accident. So the autonomous vehicle should slow down. Okay. So the policeman is asking all the cars to stop. or halt at a particular location, maybe on the side of the road. And from that, the current autonomous vehicle also would like to slow down, stop. This is an example of postulation. And anupalabdhi, non-perception, knowledge from the absence. So autonomous vehicles should be able to deal with faded lane. Okay, the vehicle should maintain its own lane, but the lines are faded. Anupalabdhi. And missing traffic light. The traffic light is missing, but still it stops at the crossing. Right? These are the things needed for autonomous vehicle, and they seem to be corresponding very well with Indian classical inquiry into knowledge. Okay. Now, your task would be to see how natural language processing would like to make use of this Indian investigation. What are you seeing on the screen? Microsoft 365? Oh. Okay. Now, two or one? Once again. Okay. So this is the end of discussion on ChatGPT giveaways and Pramanas. Let's skip it. Now let's go to an extremely classical topic, the central limit theorem. We have been mentioning central limit theorem many times in the context of hypothesis testing. After all, what it is. Statement of the central limit theorem. Theorems have to be very rigorously stated. Let x1, x2, x3, xn be n independent random variables. So all this actually should be done on the board. Okay. There are many things to cover. So I'll go through them fast, but all of these are quite clearly written on the slides. Let x1, x2, x3, xn be n independent random variables, each with mean mu and variance sigma square. And also let Sn equal to x1 plus x2 plus x3 up to xn. Then the following is standard normal. That is the theorem. That Sn, which is the sum of these random variables, minus n into mu, okay, n into mu, divided by sigma into root n, is a standard normal variable. In other words, the sum of these random variables is also a normally distributed random variable with mean equal to n into mu and variance equal to n into sigma square. So that is the theorem. Is the theorem statement clear? That the sum is a normally distributed variable. And what is more is that the mean of that new normally distributed variable is n into mu, and the standard deviation sigma into root n is for the sum. Now we can do some mathematical adjustment on this. Sn star is a standard normal variable. What we do is that we divide, okay, we divide the right hand side by n. Right hand side, denominator and numerator both by n. Then Sn by n is x bar. It is the mean of these n variables minus mu, and the denominator is sigma by root n. Then we come to an alternative equivalent statement of central limit theorem. Let x1, x2, x3 up to xn be n independent random variables forming a sample from a population with mean mu and variance sigma square. Then the sample mean itself is normally distributed, which is very nice. The mean sample mean is normally distributed with mean mu and variance sigma square by n. But for the sum of random variables, which is also a normally distributed variable, the variance is n into sigma square. For the mean, the variance is sigma square by n. These things should be noted. Now, central limit theorem, proving of central limit theorem requires definition of MGF, which is moment generating function. Moment generating function is defined this way for x, which is a random variable, and x has a probability distribution p, f, let's say. Fxj is probability that x is equal to xj. The moment generating function is defined to be the expectation of e to the power tx. Okay, t is a parameter. For discrete distributions, the moment generating function mxt is sigma j equal to 1 to n e to the power t xj fxj. So, so you can see this is fxj is the probability distribution for x, and the quantity is e to the power txj. It's a function of t. Okay, j equal to 1 to n. And for continuous distributions, the summation will be replaced with integration from minus infinity to plus infinity. Now, what is the significance of MGF, the moment generating function? The nth derivative of the MGF at t equal to 0 gives the nth moment of the distribution of the random variable. The significance of moment itself is the following. The first derivative at t equal to 0 gives the mean of the distribution. Okay, so from the moment generating function, you can get the mean by taking the first derivative of the moment generating function and making t equal to 0. The second derivative at t equal to 0 minus the first derivative at t equal to 0 gives the variance. Okay. Similarly, the third derivative at t equal to 0 along with the lower derivatives combined with proper operators at t equal to 0 gives the skewness. That is how symmetric is the graph about the mean. Fourth derivative at t equal to 0 similarly can lead to what is called kurtosis. How heavily the tail of the distribution differs from the tail of the normal distribution. So moment generating function is a very powerful concept, and it can give rise to all these parameters of a distribution which we are interested in: mean, variance, skewness, kurtosis, everything. So proof regarding the nth derivative and nth moment. So let's take the first derivative of the moment generating function, m dash xt, ddt of expectation of e to the power tx. Expectation of e to the power tx is called the moment generating function. So we have the result that derivative of expectation is expectation of derivative. So the dt of e to the power tx is x into e to the power tx, expectation thereof. Make t equal to 0, you see you get ex, expectation of x. So first derivative with t equal to 0 gives me the mean. You can get the moment generating function. Take double derivative, ddt of m dash t. So ddt of m dash t we have derived already is ddt of expectation of x into e to the power tx. So expectation comes out ddt of x e to the power tx, which is equal to expectation of x squared e to the power tx, which is equal to e to the power x squared at t equal to 0. Now we know that expectation of x squared minus square of expectation. Expectation of x squared minus square of expectation gives me the variance. And indeed, we get m double dash x at 0 minus m dash x squared, giving me the variance. Okay. So from moment generating function, we get all these parameters of a distribution. But in the context of central limit theorem, The another theorem is very important. This is called the uniqueness theorem. So uniqueness theorem states that if x and y are random variables having moment generating functions as mxt and myt respectively, then x and y have the same probability distribution if and only if mxt equal to myt. So if moment generating functions are equal, the random variables also will have same probability distribution. So two random variables x and y have same normal distribution if they have the same moment generating function. And if two random variables have the same moment generating function, then their probability distribution has to be same. What is the application of uniqueness theorem? The application of uniqueness theorem is to show if a random variable follows a particular distribution. Here is the example. Standard normal distribution. Okay, let us see what the moment generating function of standard normal distribution is. So the normal distributions, the normal distribution function is 1 by sigma square root of 2 pi e to the power minus y minus mu square by 2 sigma. Sigma standard deviation, mu mean. So we know that for standard normal distribution, mu equal to 0, sigma is 1. So I get that the standard normal distribution form as 1 by root 2 pi e to the power minus y square by 2. What is the moment generating function of standard normal distribution? Okay, so the methodology is that we have to introduce e to the power ty and the probability distribution. So why we are saying is following standard normal distribution with mean 0 and sigma 1. So we have to take e to the power ty, multiply it by its probability distribution of y, which is standard normal distribution, and do the integration from minus infinity to plus infinity. To look at the integration step, we have 1 by root 2 pi e to the power minus y square by 2 plus dy. The exponents are added. And then a bit of algebraic manipulation. E to the power minus half y square minus 2yt plus t square. This t square is subtracted. Therefore, you have to add it t square by 2, which is e to the power t square by 2 dy. Then e to the power t square by 2 is a constant, doesn't depend on y. It comes out of the integration. So we have 1 by 2 pi e to the power minus half y minus t square dy. Y going from minus infinity to plus infinity. Now, e to the power minus half y minus t square is itself a normal distribution with mean at t and standard deviation 1. Isn't it? Okay, so the integration from minus infinity to plus infinity for any normal distribution must be 1, the area under the normal curve. And therefore, beautifully, the MGF of standard normal distribution comes out to be e to the power t square by 2. Very nice. So now if I want to show that some random variable is following standard normal distribution, then I just have to show that for that random variable, the moment generating function is same as that of standard normal distribution, namely e to the power t square by 2. So this is the proof of CLT. To prove that Sn star, which is equal to Sn minus n mu by sigma root over n, is standard normal distribution, we'll have to show that the moment generating function of Sn star is same as the moment generating function of the standard normal distribution. So these I have done, okay, step by step, carefully, systematically. If you follow the steps, I'm sure you'll get the proof. It makes use of Taylor series expansion and then puts and writes down the assumption. And then finally, we come to a situation that when n tends to infinity, the moment generating function of Sn star becomes e to the power t square by 2. Okay, this is very clear. The log of the moment generating function is t square by 2. Look at the proof step by step, all very clear. So that finishes one very classical topic, namely the central limit theorem. If you remember, in the beginning of the course, we said that NLP rests on two pillars, linguistics and probability. And the probability itself is resting on two pillars for NLP and ML, central limit theorem and law of large numbers. Here is the next pillar. The larger the number of observations, the more accurate the probability value. How do we get this confidence? Okay. If we go on increasing the observation, we have more and more confidence in the probability value. For example, a hidden Markov model-based post-tagging. Suppose we get the transition probability as probability of n given jj is 0.8. The probability of a noun following an adjective is 0.8. Okay, how much confidence do we have in this probability value? And this transition probability is critical for post-tagging. It better be very good, that probability value. Can we trust this value? We can, if it is computed from a large amount of data. So we have been following our intuition that increase the amount of data, your confidence in the probability value will increase. This is based on what? This is based on law of large numbers. So we create estimates from sample, and we then make claim about the population, which is facilitated by central limit theorem and law of large numbers. This is the foundation for any probability-based work. The intrigue of law of large numbers is the following. Even though it is very intuitive, it is actually very intriguing. I do not, and most often I will not know the population average. Also, it is impossible to look at the whole population. Still, I'll converge towards it. So, don't you find it wonderful? I do not know what that value is, but I'll converge towards it. Okay, and as I increase the amount of noun and verb in the corpus, and if the value is hovering around 0.8, the values are very close to 0.8, then with very, very high confidence, I can say that the probability of noun following an adjective in any corpus will be 0.8. I get the confidence from law of large number. To this point, I find it very exciting. You should also, that I do not know the value, but I converge towards. So there are two versions of the law of large numbers. The first is weak law of large numbers. Let x1, x2 up to xn be a sequence of independent and identically distributed random variables, each having mean exi equal to mu. Okay, remember that expectation always refers to the population behavior. Expectation is a population behavior. Okay, sum divided by n is a sample behavior. Then for any epsilon greater than 0, the probability that the difference between sample mean and the population mean will be greater than 0 tends to 0 as n tends to infinity. This is the weak law of large number. So the plain and simple statement with respect to this expression is that as we increase the amount of data, amount of observation, the sample mean, as the sample size becomes bigger and bigger, the sample mean approaches the population mean. Okay, so this is called the weak law of large numbers. So are you observing the probability expression? Say that there is a difference between sample mean and population mean, and the probability is an event happening. What is that event? That difference is more than an epsilon quantity, small quantity, which we have fixed. That probability will tend to 0. The difference being more than something will tend to 0 as n tends to infinity. The strong law of large numbers is the following. Let x1, x2, xn be a sequence of independent and identically distributed random variables, each having mean exi equal to mu. Then the strong law is much simpler. It says that the probability that the sample average x1, x2 up to xn by n minus mu tends to 0, which means the sample mean tends to population mean, that probability is 1, okay, as n tends to infinity. So the population mean, that is the sum and subfield. Now, there are intricate, mathematical arguments. Probability theorists make that argument. Statisticians make that argument. Do we really need two versions of weak law and weak law and strong law? Do we need both these? Okay, those are intricate arguments. At this point, let us not be concerned about that. But you can see that the strong law is much more understandable. Okay, probability approach is 1. It's not saying it will be equal to 1. It says that most probably it will be 1. Okay. So important implication, important statement. Since the difference between x1, x2 up to xn by n and mu can be made as small as we like by taking more and more data, the intuition for large data requirement is established now. And n tends to infinity means large amount of data. x1, x2 up to xn by n tends to mu as n tends to infinity. Because of law of large numbers, I can take x1, x2 up to xn by n as the population mean as n tends to infinity. So it is very empowering. It tells me that take a sample mean as the population mean. You will be safe. Important. I need not and cannot know mu in almost all cases. This is surely true about language properties. The role of probability, the strong law of large numbers demands the probability to be equal to 1. Weak law of large numbers gives an amount of flexibility through the introduction of epsilon. So now, the proof of the law of large numbers makes use of what is called Chebyshev inequality. It says that the probability of the distance between a value of a random variable and the mean to be being greater than k, some integer k, some value k, is less than or equal to sigma standard deviation square by k square. This is called Chebyshev inequality. There is also this inequality which is famous, Markov inequality. If x is a random variable that takes only non-negative values, then for any a greater than 0, probability that x is greater than or equal to a is less than expectation of x by a. The mean of x divided by a, which is also very nice. And then the Chebyshev inequality can be proved using Markov inequality. Another form of Chebyshev inequality, which is important for us in terms of hypothesis testing, is the following. The probability of a random variable differing from its mean by more than k times standard deviation is bounded by 1 by k square. Okay, so as k increases, this probability becomes smaller and smaller. So, so see the interestingness of this statement. The mean seems to attract values towards itself. No, mean has an attractive power. As you take values, the probability of the value being far away from the mean is low. And more precisely, the distance of the value of the random variable being greater than or equal to k times standard deviation is less than 1 by k square, less than or equal to 1 by k square. So mean is a very powerful attractor. It doesn't allow the values to be far away from the mean. So that is a strange statement. After all, mean is a consequence of the values. Okay, right? Mean is a consequence of the values. And what values? The values that you are seeing from the sample. So completing the proof of weak LOLN, the expectation of x1, x2 up to xn by n is equal to mu. Variance is V x1, x2 up to xn by n is equal to sigma square by n. So now apply Chebyshev inequality. So probability of x1 plus x2 up to n by n minus mu being greater than epsilon is sigma square by n sigma square n epsilon square is due to Chebyshev inequality. As n tends to infinity, the above p tends to 0. So the weak law of large numbers is proved this way by means of Chebyshev inequality. So Chebyshev, Markov, these are mathematicians from Russia, Eastern Europe, and so on. A lot of probabilistic insight came from that region. Okay. Yeah. Yeah. 17th, 18th century was actually a very, very golden period for Europe. It gave so many things to the intellectual world. Let's begin. Um, let's start dependency parsing. Surely a very fundamental topic of natural language processing. No NLP course is complete without dependency parsing. Now, dependency parsing is older than constituency parsing. Please stop talking. Yeah, please stop talking. Dependency parsing is older than constituency parsing. Dependency parsing comes from the observation that words tend to pair up. Okay, Ram saw Sham. Who saw Ram? What did he see? Sham. So these kind of relationships exist between pairs of words. Okay, so this was observed in language and was studied systematically. Now, these pair of words having mutual attention for each other is the self-attention of transformers. Okay, you can take my word for it. So the intuition behind attention mechanism, modeling it, learning it from data, modeling it and learning it from data, modeling, not modeling. There is no mathematical expression for attention. There is a neural network. If you do not have a mathematical expression, you typically introduce a neural network, a learning mechanism. So a neural network for capturing attention and learning it from data, that is the essential feature of transformers. Okay. And can you please pay attention? These are important topics. What's going on? Okay. So attention, attention as a phenomenon, as a language phenomenon, was observed, millennia ago. You see reference to this in work of Indian linguistics, Greek linguistics, maybe Chinese linguistics also. Okay, this was observed thousands of years ago. The modern contribution is to take that phenomenon, casting it into a neural network, setting the parameters of that neural network from data. So this we are going to do from in the next semester very carefully. Attention as a linguistic phenomenon and its realization on neural network. So dependency parsing means X depends on Y. So we have already introduced it briefly. The modifier depends on the head, right? Modifier depends on the head. So blue sky is a noun phrase. Head is sky, and blue is the modifier. Depends on the head. So if we take this the sentence, the strongest rain shut down the financial hub of Mumbai. So we get the post-text sentence. The is a determiner. Strongest is JJS, superlative adjective. Rain is NN, noun. Shut, VVD, past tense, now past tense verb. Down is RP, particle. The, determiner. Financial, JJ, adjective. Hub, NN, noun. Of, IN, preposition. Mumbai, NNP, proper noun. This has less entropy than the raw sentence because the past tense uncertainty is reduced, like for rain. So rain can be verb and noun both. The perplexity score of a past tense corpus should be less than the perplexity of raw sentence. This was a mid-sem or end-sem question last year CS626. Okay, and the proof is also rigorously given. Constituency parts, we have sentence. Under this, we have noun phrase, verb phrase. Constituency parts you're familiar with already. The strongest rain is a noun phrase under NP. VP has the rest of the sentence. The VP is shown here. The VP has another VP within it. Is that allowed? Yes, recursive rules are allowed. Shut down is a verb phrase. And then we have the NP, the financial hub of Mumbai. This is also recursive. There is a noun phrase within a noun phrase. Financial hub is a noun phrase. Of Mumbai is a preposition phrase. These two together form a noun phrase. So all this is by way of reminding you that this is the constituency parts. This further reduces the entropy. Okay, so as we begin to build structures on the raw sequence of words, going up the NLP stack, we progressively reduce the entropy. The dependency parts will be in the following form. Shut is the main verb. So that's why you have a link from root to shut. Then shut has a n subject, nominal subject, noun subject, which is rain. So now we have started dependency parsing. Let's see an example of dependency parsing. So for shut, the n subject is rain. What shut? Rain shut. PRT is particle shut and down. So shut and down have a relationship between them. This is PRT, particle. There is a relationship between rain and the, is DET, which is determiner. A mod is adjective modifier, strongest rain. See that the second argument in the dependency relation is modifier. The first argument is head. Rain, shut. Okay. So down is a modifier for shut in the form of particle. The rain. Which rain? Some particular rain. So that's why the is a modifier for rain. Rain has an adjective modifier, a mod, which is strongest. Strongest is the adjective. Then DOVJ, direct object. Shut. Shut what? Shut the hub. What kind of hub? The hub, a particular hub. Also, that hub is the financial hub. That's why adjective modifier. So as I'm reading, I think your eyes are following the right places, right? So see that the third line in the second column is a mod. Then hub is linked to of by preposition. And the preposition takes an object, which is Mumbai. So hub of Mumbai. If I look at these two dependency relations, pref and POBJ, I can form a constituent. Hub of Mumbai, these two relations together give me that constituent phrase. Okay, so this is how the dependency parts is expressed. A very important topic of NLP, very fundamental. Do you have any question on this expression? And by observation, you should be able to find the constituents from the dependency parts. Now, examples to illustrate difference between dependency parsing and semantic role leveling. Dependency parsing is not semantic role leveling. Semantic role leveling is deeper. Okay, what is the proof? If we have the sentence, if it's a set of sentences, the first sentence is John broke the window. The shallow relationship from dependency parsing is N subj. Okay, so John and broke has the dependency relation of N subj. And the deeper relation from semantic role level is agent. John's role in this sentence is it is an agent. It can cause something. Then you have a sentence of very similar structure. The stone broke the window. It's a peculiarity of English language. You try to translate these sentences into your mother tongue, you will see the difference that surfaces for these sentences. Okay. Again, the dependency relation is N subj. But the deeper relation is that it is an instrument. The stone is an instrument. Somebody had to use the stone to break the window. By itself, it's correct. The window broke. Again, the relation is N subj. Everywhere the relation is N subj. But the deeper relation is different. And a good test for this is translation into your mother tongue or any other language. So Hindi native speakers, can you help me with the translation of these sentences? John broke the window. John ne khirki toda. Is it correct? Achha. The stone broke the window. पत्थर से खिड़की टूटी. पत्थर से खिड़की टूटा और टूटी. Hindi native speakers. Tutti. The window broke. Khirki tutti. Right. And see that John say, you did not have John say, but you have Patthar say. So that indicates that deeper semantic role is different. 1947 saw the freedom of India again and sub. But the relationship is time between C and 1947. So 1947 में भारत को आजादी मिली. Delhi saw bloodshed when Nadir Shah attacked Delhi. So again in subj, and the deeper relation is place. When जब नादिर शाह दिल्ली पर वार किया, तब दिल्ली में, what will be the Hindi? Loudly. खून खराबी हुई. खून खराब हुआ. So you see, Delhi में 1947 में खिड़की पत्थर से John ने. Okay, all these indicate that the deeper relation is different. Yeah. Oh, we have. John ने खिड़की तोड़ दी, पत्थर से खिड़की टूट गई. खिड़की टूट गई. 1947 में भारत को आजादी मिली. जब नादिर शाह ने दिल्ली पर हमला किया तो दिल्ली में खून खराबा हुआ. Different. India signals for semantic difference through case marker. English is more ambiguous, but English sentences are more metaphorical. You see that? It's more metaphorical. 1947 saw. How can a year see? That usage is metaphorical. Delhi saw. How can a place see? Metaphorical. People of the place saw. People living in that time saw. Okay, a computer has to understand that. This was a tremendous challenge pre-LLM. Now give these sentences to ChatGPT. It will very easily process this sentence. It will also tell you And 1947 saw is a metaphorical use, Delhi saw is a metaphorical use. NLP has come a very long way. So two kinds of parse representation. S goes to NPVP, where constituents are captured one by one. Dependency parsing is centered on main verb. If you recall, I had drawn a picture on the board of a stage. So the main verb is the stage, and the noun phrases therein are actors relating to the stage. So some of the important sources of data are Penn constituency tree bank, which is used for constituency parsing, and Prague dependency tree bank, which is used for dependency parsing. They were used to train machine learning model for doing dependency parsing, constituency parsing, and so on. So this sentence we have seen umpteen number of times. I saw a boy with a telescope. It has two parses. And it has two dependency parses also. So what is the advantage of dependency parsing over constituency parsing? Related entities are closer in dependency parsing than in constituency parsing in terms of path length. Okay, related entities are closer in dependency parsing. Let us see. Saw a boy. See the distance between saw and boy here. Many arcs between saw and boy. But here, directly, saw and boy. Pre-word order doesn't affect dependency parsing. Constituency parsing needs additional rule. Okay, pre-word order really derails the constituency parsing process. And additional rules actually may overgeneralize, and it can admit wrong constructions also, because new rules have come in. I saw the boy with a telescope. S goes to NPVP, VP goes to VBD, NPPP. With a telescope, I saw the boy. You need this rule. S goes to NPVP, and S goes to PP, NPVP. You need additional rule. Okay, and this additional rule is creating a chink in the armor. It is creating a hole in the armor, okay, through which wrong entries can enter. So impact of pre-word order on constituency parsing. Constituency parse fundamentally uses adjacency information. Word order disturbs the adjacency. Chomsky normal form demands that the deduction should happen by linking together two adjacent entities. Okay, Chomsky normal form always has at most two things on the right-hand side of a rule. Ram ne sham ko dekha. Sham ko dekha is verb phrase. Sham ko Ram ne dekha. Now the verb phrase has become discontinuous. So Ram ne sham ko dekha is a verb phrase. Sham ko Ram ne dekha. Sham ko, piece of text, discontinuous, dekha. Okay, so constituency parser will run into difficulty here. The agent and object are reversed in the above example. So constituency parsing needs additional rule. Constituency parsing is really very English-centric, or any language which has fixed word order of language. So in case of dependency parsing, the arguments are immediately linked. This sentence is a famous sentence from Jurafsky and Martin. I prefer the morning flight through Denver. I prefer the morning flight through Denver is the first dependency tree. Prefer is the main verb. Who prefers? I. What do I prefer? Flight. What kind of flight? The morning flight. Little more specification through Denver. And the other sentence is, I prefer the morning flight through Denver. So this is the constituency parse tree. It seems more cumbersome. It has many more nodes, and the structure is complex. So an interesting question is how to measure the complexity of parse trees. So in terms of arcs and nodes. So constituency parse trees typically have more nodes than the dependency parse tree. And the answer is quite intuitive. Why do you think it is so? Why do constituency parse trees have larger size than dependency parse trees? Isn't the answer obvious? Why this silence? So dependency parse tree straight away uses the terminal symbol, the word. Constituency parse trees introduce non-terminals, which are not part of the sentence. They're hidden. So again, some kind of hidden Markov model will uncover this non-terminal. What kind of hidden Markov model? The probabilistic context-free grammar, which we did before midterm. Okay, this is also an exercise in uncovering the hidden variable. Now, dependency relations are also standardized, just like part of speech stack. There is this universal dependency project by Nivre et al. 2016. So they very carefully document all the dependency relations, all useful dependency relations. They depend on what? They depend on language phenomena, first of all. There are subjects, there are complements, direct objects, and they depend on computational phenomena, because these labels are to be used in machine learning model. And the machine learning model should find it easy to deal with these levels. Their accuracy should not fall. If it is very fine grained, it will be impossible to reach high accuracy. If it is very coarse grained, then subsequent NLP applications which make use of dependency parsing will suffer. Right. So, for example, dependency parsing is used in sentiment analysis very heavily. Who has what sentiment about which part of the product? I like the camera of the phone, but not the color. Okay. So dependency parsing is inherent in this problem. So all these levels reflect language phenomena and also computational phenomena. It is not easy to come up with a set of classified levels if you have machine learning in mind. So n sub is nominal subject, Ram saw Sham. D obj is direct object, Sham is the direct object. I obj is indirect object. Ram gave a book to Sham. Here, book is the direct object for give, and the beneficiary is Sham, so indirect object. C comp is clausal complement. X comp is open clausal complement. Okay, we'll take example for many of them to illustrate the language phenomena. N mod is nominal modifier. Nominal modifier example is cricket bat. Cricket is modifying bat. A mod is adjective modifier, blue sky. Num mod is numerical modifier, 5 children. Date is determiner, the boy. Case is prepositions, postpositions, and other case markers. So prepositions have linkages with nouns. And other notable relations, conj is conjunct. Okay, he sings and she dances, for example. CC is coordinating conjunct, which links phrases. Ram sings and dances. So n sub d obj I obj, Ram gave a book to Sham. C comp X comp, I said that he should go. The same meaning can be expressed by another sentence. I told him to go. So in this case, said and go has what is called C comp level, and told and go has X comp level. If the question is why not why not have the same level, same C comp for both? The problem is that to is a very deceptive preposition. Okay, to can link many kinds of part of speech, which can lead to ambiguity and also a problem for machine learning algorithm. So all these, by the way, you must appreciate this point. All these are very intricate exercise in both linguistics and machine learning. Please appreciate this point. That is, in fact, a very important message of the whole course. All these are very intricate, detailed investigation into linguistics and learning. So C-comp links the main verb with the finite verb. If there is a notion of finite verb, a language phenomenon. XCOM links the main verb with an infinite verb. Infinite verbs do not take any modifications. Okay, go, going, come, coming. These show that the verb is finite. They take modifications. Infinite verbs never take modifications. So the verbs which come after two are always in non-finite form. Finite verb means takes GNP time marking, gender, number, person, tense, aspect, modality marking. Infinite verbs remain in the lemma form, basic form. Told him to go, go will not change from infinite form. Said he should go, be going, go can change the form. Okay, so this. So, all right, so we'll go on with the relation levels going forward. Let me finish the class today with reminding you that on 24th, you have a quiz. The quiz is from mid-sem up to today, whatever has been covered. End-sem will cover everything. And this week, we'll have one extra lecture on Teams. Next week, two extra lectures again on Teams. All the lectures will finish on 3rd. Okay? And you probably have got the announcement for demonstration of the SVM NEI assignment, and also your preliminary project discussion and final project discussion later. All of you, please fix your course project. Course project has considerable weightage. Okay, thank you.